Hello, welcome to our project presentation. My name is Claudio Moiwa and we are students from Siemens Center at Dedan Kimathi University of Technology. We are working under the supervision of Professor Jean Bosco. The project we're presenting today is the development of a digital twin from the FESTO distribution station. It's an integrated industrial 4.0 system encompassing PLC control, mechatronics simulations, industrial communication, and a web-based manufacturing execution system. Allow me to briefly introduce my team members and their respective contributions.
I am Brian. I was responsible for MES integration and developing the web application.
Hello, I'm Brian Mangala. I helped in the development of the communication system in between the physical system, the digital twin, and the website.
And I developed the digital twin in Siemens NX Mechatronics concept design, as well as the integration layer connecting it to the PLC. We will now take you through each component systematically. Let us begin. Now this is a physical station of our project. It's a 3-magazine sorting station. It has a red, black, silver part. The silver being a metallic part, the red and the black are plastic parts. The magazine pushes the workpiece onto the conveyor, in which the conveyor moves the workpiece to the delivering point. Now on this conveyor we have two sensors. We have the color and the material sensor, which is a capacitive and inductive sensor. We have our safety features here, which is the safe light curtain and the safety relay, which work in tandem. We have a light tower, which is used to show the state of the machine. We have a flow sensor, and we also have a compressor. Now the station runs on a PLC 1200. We used to use a 1500, but we switched to 1200. We also have our HMI panel over there. Yeah, that's everything on there. For the control logic, the PLC was programmed into your portal using ladder logic. It has a modular structure to improve troubleshooting and scalability. So the main execution cycle is managed by the main OB1, which continuously scans inputs, executes logic, and updates outputs. During startup, the startup OB100 initializes all variables, resets outputs to safe state, and ensures the system begins from a known condition. Over to the initializing block. It plays a key role in the system control by handling all operator commands. It processes start, stop, order inputs coming from both HMI and the web interface, as you can see here. It also controls the HMI order patterns. So then once the system is enabled, the sorting routine is executed through dedicated function block. As you can see here, we have the 3 green blocks: the initializing, the process black, the process red, and the processing silver. Each one of this block contains a logic specific to the respective part type. So the processing black only works with the black magazine, the processing red works with the red magazine, and the processing silver works with the silver magazine. Then the machine state control block coordinates the entire process using a state machine approach. It controls the sequence of operation from idle, detection, classification to actuation. It ensures that only one step occurs at a time. Then we have our data blocks. The data global parameters stores the data which is used by the OPCUA to communicate through, in order for clients, OPCUA client, to access the data. Yeah, thank you. Let's move on to the HMI. So here's our HMI. We have our start, stop, reset, order, and web buttons. We also have our addition and subtraction for the red, black, and silver parts. We have our data. At the right side, which is the ordered parts, the delivered parts, and the rejected parts. And we also have our status notification at the bottom. So let's say we want 1 red, 2 blacks, and 1 silver. So we can start the operation. See the light turns to green, then we can order the parts. I'll now walk you through the digital twin we developed using Siemens NX Mechatronics Concept Designer, or MCD for short. The objective was to create a virtual replica of the FESTO distribution station that mirrors the behavior of the physical system. So first we began by creating the 3D model of the sorting station, ensuring that all of the mechanical components were accurately represented based on the physical setup. This includes the magazine, the conveyor, the sensors, the base, the pressure regulator, the flow sensor, the stand which holds the transmitter and the receiver, and we also have the safety relay and the light tower for safety purposes. After completing the 3D model, we imported it into NX MCD, which is this one. So here we define the physical behavior of each component, assigning the mass, the collision geometry, the material properties in order to ensure realistic simulation. Then we also define joints and constraints. So for actuation, each pneumatic cylinder was configured as a linear motion joint, while the conveyor was implemented as a transport surface. The motion limits and speed were carefully mapped to match the real system, ensuring synchronized and accurate movements, like I'll show right now. If you go here, we were able to move each magazine, and this, you can see they have limits. They can't go past that, and they can't retract past that. We also have the conveyor which is being moved by the gears forward and also reverse. Yeah. Then finally, we established signal mapping between the digital twin. So we established signal mapping here. We established signal mapping between the digital twin, which is this side, and the PLC, which is PCUA server, which is this side. Each simulated input and output is directly linked to the corresponding tag, the red extend, the black extend, the end sensor. Yes, red present. This enables real-time interactions. When the PLC commands a cylinder to extend, the digital twin responds instantly. It maintains a synchronized control system. So this integration ensures the digital twin behaves as a true representative of the physical station. Now I'll hand it over to Brian, who will explain the OPC-UA communication layer in more detail.
Hi, I'll take you through the communication layer that ties the entire system together, which is the OPC-UA. The OPC-UA stands for Open Platform Communication Unified Architecture, and it is an industry standard communication protocol designed specifically for industrial automation and allows different systems, for example, PLCs, simulation softwares, and web applications to exchange data securely and in real time, regardless of the manufacturer or platform. Now, in our system, we use the S1200 PLC as our server, whereby to configure it, we had to activate the OPC-UA server to allow accessibility of the server, then set the server address, and thereafter we had to configure the server interface. The server interface allows communication with the external system, and the server interface mostly defines the nodes by exposing tags, data blocks, and user-defined types, mostly that you want exposed. Now, after doing that, we created a dedicated communication data block, which functions as a data contact. Now, this data block contains only variables required by external system, structured logically for client consumption. This means that any authorized client on the network can monitor the station state or send commands to it without any additional middleware. On the software side, a Python client using OPC-UA library connects to the PLC's endpoint using over TCP. So once it is connected, it can read any node, such as machine state, accepted part counts, rejected part counts, and write to nodes like quantity set points, button triggers, and Writing a Boolean true to a button node replicates the physical rising edge exactly as the PLC ladder logic expects. The client is wrapped in a reconnection layer, so if connection drops, it automatically tries to re-establish connection before trying to read or write. So all nodes, namespaces, IDs, and endpoint addresses are centralized in a single configuration, making it straightforward to adapt to any OPCUA-enabled controller. So the interface is hosted as a local web application, and all live data flows directly from the PLC to the OPCUA through this OPCUA connection.
So I'll be taking you through the manufacturing execution system that we made for our project. It's a simple, user-friendly web application that the user can track, monitor, and place an order in the system. On your bottom left, you can see that it is connected to our PLC. And we'll start with the dashboard. In the dashboard, there is an order number for each order that will be placed. There is an order ID for every order too. We can see the machine state and the station status while the machine is running or it is in idle mode. And you can also track the order process. Then we move to the place order tab, where the user can put the order that they want, then send the order to the PLC. Then at the dashboard, you can start the whole process in the machine. In the order process progress, you can track what is being on the machine. You can see that we have delivered one red, we have delivered one black, and also we are currently delivering the last silver. After that, you can go to the monitor tab, where you can see the total number of reds delivered, the total number of blacks delivered, and the total number of silver delivered. You can also see the total number of parts that have been rejected, and you can also see the current order as they are being you can go to the controls, where there is a start, stop, and a reset button, and also a place to configure the local host where you can open the page from. Then after that, we go to the history tab, where you can track all the orders that you have made in the past. For example, the first order, the second order, the third order, and see the parts that were delivered.
Okay, so what you're seeing right now is our complete system running live. So you can see the part order is being placed on the website, which is then sent to the PLC, which immediately starts the sorting sequence, as you can see right now. Notice the digital twin in Siemens and X on the right. Every movement you see on the physical station is being mirrored simultaneously in the simulation. So this is our system, a physical station, a digital twin, and a web-based MES, all working as one.